speaker is Julie Bergner from UC Riverside, who's going to be telling us about models of homotopical higher categories.
Okay.
Sorry.
All right, well, thanks to the organizers for the invitation. So as often seems to be the case, I end up in the position of sort of going back and explaining some things that have been secretly or not so secretly in earlier talks in the day, and sort of pulling them out and saying, hey, let's actually talk about these. So I wanted to start with just the idea of what higher categories are. So starts out very much like ordinary categories. So we have objects, we have morphisms, but I want to now call them one-morphisms. And as you expect, these go between objects. And then you just sort of continue this process. So you say, well, now between one-morphisms, I can have two morphisms. And then, well, you can keep going. At least this far, I can draw a picture. So maybe you have objects like this. You have a couple of different one-morphisms, and then you have a two-morphism between them. And then you could imagine sort of having a front and a back two-morphism, and then there's a three-morphism between them, and so on and so forth. So you could stop at some point if you'd like. So keep going and say you'd have n morphisms between n minus 1 morphisms. And in which case, you would call this an n category. That's if you were to stop. But you could also say, well, I just want to keep doing this forever and taking morphisms between morphisms. So if you keep going, this would give the idea of an infinity category. And by infinity category here, I really mean infinity category and not something I'll talk about later. So that seems fairly harmless as I've described it, but there's really a lot of ambiguity here. So if all of this is strict, so everything you expect to happen between morphisms in an ordinary category, you have associativity, you have identity maps on objects, well, you can define these things. You can compose two morphisms or 100 morphisms, whatever, with each other, and you can ask them to be associative and for identities on lower morphisms to hold and so forth. So there's absolutely no problem with this if everything is completely strict in this definition. So but the problem is that the examples of these things that we find in nature are generally not strict in some way or another. So something doesn't quite hold on the nose. So, for example, you might have, associativity only holding up to isomorphism, not actually on the nose. So you might say, well, that's not so bad, but if these things only hold up to isomorphism, well, then you need to worry about coherence conditions. So things can get rather messy and really hard to manage very quickly. So just an example that kind of came up in the last talk is that of these cobordism categories. well, there's cobordism categories and there's cobordism higher categories. So you could start, say, let's take the most basic case where you have a category whose objects are zero-dimensional manifolds. And then you have morphism, well, one-morphisms are sort of they're one-dimensional cobordisms. Well, if you even just say it just like that, you already run into a problem. So, I mean, here's a picture of such a thing. So maybe you have 3 points and 2 points, I don't know. I'll just do, okay. So something like this, that would be an example of such a cobordism. But even this, I mean, if you compose just by stringing these together, this is not associative on the nose because you're sort of parametrizing these things, and so it depends on how you're parametrizing. So it's only up to some homotopy that these are actually associative. Well, in this case, you say, okay, fine, well, I just take cobordism classes. So that eliminates this ambiguity about parameterization. You know, you still can get an actual honest category. That's fine. But what if you go up a dimension, so keep all of this, and say, well, I want some two morphisms. I want cobordisms between the cobordisms, which will give you a manifold with corners. And rather than stand here and try to draw some complicated picture, I will draw just a very simple one of these. So maybe I have this cobordism and that cobordism, and then I can just sort of fill this in with a square. I said, very basic example. I don't trust my drawing skills in public. But you can see now we're okay on our top dimension. We can say, okay, I can take cobordism classes on the level of these two morphisms, but I can't take cobordism classes anymore on the level of one morphisms. To define a cobordism between them, I need them to actually be manifolds and not cobordism classes. So this does not define then a strict two category. It's something weaker. Okay, so we really need some way to handle these. So there's lots. Now, if you're just dealing with, say, two categories or even three categories, there are definitions out there that are pretty rigorous about what these are and what all these coherence conditions need to be and so forth, and we're okay. But if you want to keep going up, there's lots and lots of definitions. I'm not even sure what the last count is, but so weak n categories, or even in the case of weak infinity categories. But there's, from this approach, almost nothing in the way of comparisons. So it's very hard to compare these definitions. So there was this workshop at the IMA in 2004, organized by Peter May and John Baez, and they had this goal of we're going to bring together all the people who like to think about this, and we're going to sit and work, and we're going to get all these comparisons done. And that didn't happen, and that was almost 10 years ago. So there's still just a lot of really, really difficult mathematics here. Now, I was maybe not so cooperative as Chris was in that I actually changed my title from what the organizers asked me to speak on, in that they said, well, they wanted me to give a talk on higher categories. And when I think of just higher categories, I think of this stuff. And I don't really know, honestly, that much about this stuff. So what I do want to talk about, and what's been sort of much more tractable, at least in being able to make comparisons and understand how the different approaches interact, are homotopical versions of these. So that leads to the idea of what we call an infinity n category. So this is maybe I should, this is mostly a heuristic definition. But so an infinity n category is a I'm mostly going to omit the word weak here, although everything should be assumed to be weak. So this is a weak infinity category, meaning that I've got objects and I have morphisms of all levels all the way out to infinity, but where the k-morphisms are invertible after some point. In fact, so for k greater than n. And again, this should be a weakly invertible. It may not have a strict inverse. Okay, so back to our cobordism example. There's an infinity n version of this. So we have things here, and, well, so we have our zero manifolds as our objects. And so somehow, so this is an infinity n, then we keep going up to sort of n-dimensional cobordisms. So cobordisms, we have no reason to assume that they're invertible. But then we want morphisms going all the way to infinity now, which are invertible. And we can do that by saying, okay, well, we're going to stop taking cobordisms here at level n, and then we're going to take, so these are our n morphisms. So then we can take diffeomorphisms of those cobordisms, and then these would be our n plus 1 morphisms. Now they're diffeomorphisms, so they are invertible, and then you can take isotopies of your different diffeomorphisms, and those would be your n plus 2 morphisms. And, well, just keep going. Okay.
I guess I'm confused. What's the sense in which a cobordism isn't invertible, but an isotopy is?
Well, they're isotopies between diffeomorphisms.
Well, maybe I'm just thinking like more naively, like.
Well, okay.
Isotopy, like if you do it backwards and you compose, it's not the identity. It's just something that could be homotopy.
Right. So I guess I want enough structure there's enough structure on my cobordisms that I'm not assuming that I can just flip them back and forth. So anyway.
With a diffeomorphism, you can produce a cylinder, which is an example of it.
Right.
Where you use the diffeomorphism at one end. So that's an example of an invertible cobordism.
But it's not literally invertible.
Well, it's weakly.
No, everything else just has to be weakly invertible. Everything
Right, okay.
weakly invertible. Yes. Yes. Yeah. No, I'm not assuming things are strictly invertible. Yeah. Yeah. Okay. But none of this is this is certainly not a rigorous definition of what an infinity n category is. So I want to basically spend the rest of this talk really talking about how we can really put this definition on a firm footing. How can we really, get our hands on an infinity n category and actually work with these as some kind of mathematical objects, do homotopy theory with them, and so on. So the best approach to these really is, well, to start at least inductively and say, all right, I want to start with an infinity zero category. So this would just be an infinity groupoid. Everything, all the morphisms of all levels are supposed to be invertible. So it's often just sort of, we basically just define, we take this as a definition and just say, well, an infinity zero category, or again, infinity groupoid, if you like, is just a, well, take your pick, whether you like topological spaces or simplicial sets. So at the very beginning here, I'm basically referring to topological spaces just to build your intuition on why this should be true. But as I go through, I'm going to be thinking much more simplically. OK, so why on earth should I think of a topological space as an infinity zero category? Well, start with, I'll just say space. I'll be very ambiguous here. What I'm going to say is much better if it's a topological space. Well, the space has points. So I want to think of the points of that space as my objects. Well, then I can, at least between some of the points of x, I can join them by paths. So I'm going to make those my one-morphisms. And since paths, well, they're not strictly invertible, but they are weakly invertible. So that's good. And then if we have two paths connecting the same points, well, we can take homotopies between them. And this will give two morphisms. And then you can take homotopies between the homotopies and, well, keep going. And so we have some kind of weak infinity category where all the morphisms at all levels are weakly invertible. So that seems sensible. Well, that's why I said, I mean, yes, if you want to think simplicial set here, then it better be a Kahn complex, yes. But OK, but I said one of the things I'm interested in doing with these things is homotopy theory. So it's worth at this point mentioning that, you know, we can do homotopy theory with topological spaces. I mean, sort of where it started, right? So, and I'm going to say we have a nice homotopy theory in the sense that we have a model category. Again, I mean, here, again, ambiguously use spaces because the model categories here are equivalent. So okay. All right. So that's what's we have no problem doing homotopy theory here. And a key property that's going to come up later that's nice to know here is that this model category is what's called Cartesian, which just means that, well, you have some kind of Cartesian product, and you have some internal Hom objects, and everything is compatible with your model structure. OK, so this suggests we have a pretty good handle on infinity zero categories. So how do we proceed? Well, a general principle in higher categories, and this really is true if we're talking about the very strict n categories, is that a strict n category is a category enriched in strict n-1 categories. So you look at an n category, you say, OK, I have objects, and then I look at the morphisms, and, well, the morphism objects form an n-1 category. And strictly, there's no problem with saying that. So sort of making sense of that for weaker definitions gets more complicated, of course. But we want the same kind of principle to hold here. So what we want is that an infinity n category should be a category enriched in infinity n minus 1 categories. So that gives us a very natural candidate then for what one model for infinity 1 categories should be. Okay, so this is our first approach. So we say categories enriched in infinity 0 categories, but those are just spaces. So again, I encourage you, well, right now to think about actual topological spaces or Orcon complexes. But why? How can I think of this? Well, now I have some category, and now I have some mapping space. So I have some other objects. So these are just some objects here. This is a space. So now the points of that space I should think of as one morphisms. So, well, but there's no reason to assume the points are invertible in general. And that's our 1 in infinity 1 is that up to the one morphisms, they don't have to be invertible, but after that they do. But now our paths between points, they've also been upgraded. So they are now 2 morphisms, and so now from level 2 on up, things are weakly invertible. And it turns out, so now I'm mainly just going to refer to simplicial sets now rather than topological spaces. Although much of this, I mean, is still okay. But so again, I have a way to do homotopy theory here. There is a model structure on these, which I'll call simplicial categories now, categories enriched in simplicial sets. Okay, so this so far looks like a really promising way to continue and say, okay, great. So we started with infinity 0 categories. We had a definition. We enriched in them. We got infinity 1 categories. So let's just do it again. Let's just take categories enriched in spaces and call them infinity 2 categories. And those are mathematical objects. You can define them. But we're going to start running into some difficulties if we do that. So Okay, so the first problem with this is going back to this question of we'd like something that we actually can find examples of. And if you recall so what does this mean? This means that our mapping spaces, mapping objects, really form simplicial categories, and they have an on-the-nose composition. Now, if you recall this morning in Andrew's talk, he talked about an instance where this happened and referred to it as a miracle. So this maybe isn't the best. I mean, it wasn't he's talking actually about an infinity 1 category, not an infinity 2 category. But you get the idea that asking for this very strict composition of enriched objects is just often going to be too much to ask for. And so this isn't going to be an optimal model for that reason. And the second reason is that we no longer have a nice way to do homotopy theory. And then that we no longer have a model structure. Well, why not? What went wrong? Well, I remind you now we had this really nice property on the category of simplicial sets or topological spaces that this model structure was Cartesian. It was sort of this extra feature of this model category. Well, it turned out that extra feature was really important in getting a model structure when we enrich in it. But we lost it. The model category of simplicial categories is not Cartesian. So we cannot expect that when we enrich in it to get a model structure at all. So we're sort of losing nice properties as we go up. So if you're like me and you really want to be doing homotopy theory with these things, this is not a good approach at all. So this suggests that maybe we ought to rethink just this sort of naive, let's just keep iterating this process of enrichment. Okay. So fortunately, we have a lot of other approaches to infinity 1 categories that are weaker in nature. They don't quite have this same strict composition on mapping objects, but maybe some kind of up to homotopy version, and we can make a little more progress when we use them. So So I will list, I guess, most of the ones we have right now. So we have quasi-categories. So these not under that name, initially were from Boardman and Vogt. Of course, better known as introduced by Joyal and by Lurie. But there's some other models. We have Seagull categories, introduced, again, not under the same name, but the idea was in a paper of Dwyer, Kahn, and Smith, and later developed more by Simpson et al. And then we have complete Seagull spaces, which are due to Resk. And then we have sort of came up, well, with a little bit of extra structure at Andrew's talk this morning, categories with weak equivalences. So I guess first, how do you say, came up on a lot of work of Dwyer and Kahn, and homotopy theory was looked at more recently by Barwick and Kahn, who call them relative categories. Okay, now, I don't have enough time to go into all the details of all of these, so I'm going to kind of take one path that will hit some of these models and talk about how we can upgrade them in nicer ways than what we have described up here to models for infinity n categories. Okay, so the main ones that are going to come up here are going to be Seagull categories and complete Seagull spaces. So let me start by at least giving you what those are. So these as basic objects, these are going to be simplicial spaces, by which I mean simplicial objects in simplicial sets. Okay, so I mean some kind of functor from delta op into simplicial sets. Okay, but then what other properties these are going to have are going to, well, we need to impose some extra structure in here. So our first definition is going to be that of a Seagull space. So a Seagull space X is a simplicial space such that the Seagull maps, so these go from xn to sort of iterated pullback of x1s along x0, are weak equivalences of simplicial sets. So this will be for every n at least 2. Now, remember, the first model we have in mind are categories enriched in simplicial sets. So you could take a simplicial nerve of a simplicial category, and you would get, well, certainly you'd get a simplicial space, and it would have 2 properties. The first, well, if we're enriching in simplicial sets, we don't have any simplicial structure on the objects. You just have a set of objects. So x0 would be discrete, and these maps would actually be isomorphisms, because if you're in a simplicial category, you have strict composition. So, so this is substantially generalized. Here we have no condition on x0, and we're only asking that we have this composition up to homotopy. Yes?
Do you have to specify those maps, or do they just have to?
No, well, I mean, they're basically induced by the, projections, but, I mean, they're induced by these maps called alpha I in delta, that go from 1 to n, where you send 0 to I and 1 to I plus 1. So you take the collection of all those and you flip them because it's delta op. And, yeah. So yeah, it's a very specific map. It's not any old map between the 6.
So in your comments now about categories was that, I mean, maybe it's hard to say, on the right side, if x1 is like morphisms,
right.
The right side is obviously change of n morphisms.
Right.
And also in the nerve, the n space is change of n morphisms.
Right. Right. So if this map were an isomorphism, that would say every time I have a, composable collection of mapping spaces, I can always, I can think of those. I mean, they always compose. So more simplistic. I mean, I have a string of 1 simplices. I can always fill it in with an n simplex. Now, this is just a weak equivalent, so you're not literally always able to fill it in with an n simplex, but close enough. Up to homotopy you are. Okay. Okay, so in this definition then, so again, we want to incorporate some of this language of categories. So we can think of having objects. This would just be, well, I really want to think about having just a set of objects. So I'll say, well, the 0 simplices of the simplicial set at level 0. And, well, then you can define mapping spaces. It's like what sits above the objects. You can also get fancier. You can define what homotopy equivalences are, and lots of other things that you like to have for categories. So the homotopy equivalences in particular, they're going to form a subspace of x1. So I'm going to call them sort of x homotopy equivalents. They're going to sit inside of x1. Some of our morphisms will be homotopy equivalences. Okay. So these are not yet, these are still quite a bit too general to model infinity 1 categories, but there are two things you can do to make them do so. So one way is that you can ask that x0 be discrete. And that is what's going to give you the definition of a Seagull category. So it's basically a Seagull space with zero space discrete. The second way, this has the advantage of being very sort of easy to describe. You get a good sense of what it is. Not very fun to deal with if you're doing homotopy theory. Sort of hard to preserve that. But we can then say, well, I want x0 to look like some moduli space of homotopy equivalences. So you can say, well, I want the homotopy equivalences to look an awful lot like the zero space. And this leads to complete Seagull spaces. Okay, and we actually have model categories for each of these. So in fact, there's actually two model categories for Seagull categories. One was first due to Pellissier, and I gave another proof and I gave another model structure, and then this model structure is due to Rusk. In fact, the whole definition of Seagull spaces, complete Seagull spaces, are due to him. So in pink here, so this is model categories. Okay, and then, in fact, we claim that these are infinity 1 categories, and you say, well, in fact, they do. So these model categories are equivalent to the model category for simplicial categories. And there's lots of details there I'm ignoring. Okay, but one nice thing about the model structure is actually true for Pellissier's model structure on Seagull categories, not true for the other one. But one nice thing about Rusk's model structure for complete Seagull spaces, it is in fact Cartesian, which makes us very happy because we have some hope that we can enrich in it and get a model for infinity 2 categories. Okay, so that seems like it's solved our problem, but if we try to iterate it now again, we're going to have the same problem that we had before. We don't expect the model category of categories enriched in complete Seagull spaces to be, we wouldn't expect that to be Cartesian, and so we're going to run into the same kind of problem. So what we really want to do then is take maybe one of these other models and try to come up with higher versions of that model that are always Cartesian, and then we could sort of compare to some enriched thing and sort of justify that they're really models for infinity n categories. So what we really want here is somehow some higher version of complete Seagull spaces. Okay, so the way we're going to do this is when we had complete Seagull spaces and such, we have some functor from delta op into simplicial sets. And if you think about the objects of delta op, you're looking at little strings of arrows. So these are sort of parameterizing all the things that could happen in a category, right? You can have an object, you can have a morphism, you can have composable morphisms, you can have longer strings of composable morphisms. It's all sort of built into the structure of delta. So we could ask then, well, maybe I want some kind of indexing category such that if I take functors from it into, I want to take functors from it into simplicial sets, but I want another category to sort of parameterize all the things that could happen in a higher category. Strictly, maybe. But then when we're mapping into simplicial sets and we have these weak conditions, it won't be so strict anymore. So the way we're going to do this is using something called the Theta Construction. So the construction I'm going to describe is originally due to Clemens-Berger. So we're going to start with a category, C, and we're going to define another category called theta C. Okay, so I guess that's a script C. So define theta C. So this is going to have objects that look like, say, M, C1 up to Cm. So M here is an object of delta. Okay. And these CIs are all objects of the original C. So one way to visualize these objects is, so maybe you have, so here's your object M in delta, and then you have M arrows here, and so you label these arrows by these objects of C. So what's a morphism? It's one of those things that's much more enlightening to look at an example and to write down the actual definition. So let me just give you a couple of objects here. So maybe I have this object. I'll make it a little longer. Okay. So maybe here I have some C1 up to C4. And then down here I have maybe D1 up to D3. So this is first going to be given by a morphism in delta from 4 to 3. So maybe I like this one here. Okay. So that's the first piece of information. And then wherever it makes any sense to have morphisms between objects of C, I have them. So here, this is the most straightforward case. I'm going to have a morphism here between C3 and D3. And here, you say, well, that's a little confusing, but it turns out I have two. I have a morphism from C2 to D1, and I have another morphism from C2 to D2. And C1 and C4 here just kind of get squashed, so there's no morphisms out of them at all. Okay, so what does that have to do with what we're trying to do? Well, we're going to define a bunch of categories called theta n's. Okay, so we're going to define theta 0 to just be the not very interesting category with one object and an identity morphism. And then we will define theta n to be theta of theta n minus 1. So the first thing to notice is that theta 1 is actually equal to delta. So I take an object of delta, and I label the arrows by objects of delta 0. Well, there aren't a lot of those. There's not much going on. This is just delta. What's more interesting is, well, what's going on in theta 2? Well, let me give you an example of something in theta 2. So here's a typical kind of object. So I have something in delta, but, right, this is theta of delta, theta of theta 1. So my objects here will also be objects of delta. So maybe I take 1, 0, 2. Okay, let me draw that like I had over there. So I'm labeling these 1, 0, 2. But, okay, here I was thinking of an object of delta as some string of arrows. Well, these can also then be interpreted as strings of arrows. So I can draw this as, well, here I have something that looks like a 2 morphism. Well, this isn't very interesting. It's just a 0. And then I have a 2. Well, this is really looking like sort of a baby model of some kind of 2 category, or something that generates a 2 category. And you can imagine that if you then take theta 3 and so forth, you'll get models, little things that look like nice little n categories. Okay, so now we can define roughly what our higher order complete Seagull spaces are going to be. So a beta n space is a functor, say x, from theta n op to simplicial sets satisfying Seagull conditions and completeness conditions at all levels. And that gets very technical to write down exactly what that is, but you should think of, well, these same kinds of things that happened in the definition of complete Seagull space, that should still hold. You should have some kind of weak composition, and then you have some sort of, I mean, the completeness gets maybe even less clear than it was in the original case. But it's something that you can do. And then, so this was defined by Charles Rask. And he was able to prove that these have a nice Cartesian model structure. So that's very nice. We not only have a model structure, it's Cartesian. We have some hope for any n here. We could imagine enriching in it and saying, okay, well, does that, if I enrich in theta n minus 1 spaces, does that give me something equivalent to theta n spaces? And that was, in fact, Charles's conjecture in that paper. Yeah, so, okay, I'll go back to like this example here. So if you had some x of this guy, so sort of one level of Seagull would say, well, this had better look like x of this guy crossed over x of a point x of this guy, again, crossed over x applied to a point to x of that. Well, and then, so that's one level. But then the second level, there's not much else I can say here. But then this guy should look like x of this guy crossed over x of that guy, x of another one of these guys. So, yeah. Okay. So the conjecture is that, so categories enriched in theta n minus 1 spaces, so this should be equivalent to theta n space, where these are the model structures. Okay. So let me finish by just saying where we're at in that process. Okay. So let me go back to the n equals 1 case. What this string looked like, we had categories enriched in simplicial categories. Then we had some Seagull category model structure. So this looks like some functors from delta op to simplicial sets, satisfying some Seagull condition and some discreteness condition. And, well, there's actually 2 model structures there, but I'm not going to write them both down just in the interest of time. And then I have complete Seagull spaces here, which look like functors from delta op into simplicial sets satisfying Seagull and some completeness condition. So the general case should look, now I should have theta n minus 1 categories enriched in theta n minus 1 spaces. I should have some kind of Seagull version. So I have functors from delta op into theta n minus 1 spaces satisfying Seagull and discreteness. Then I'm not going to be done quite yet. I'm now going to have functors from delta op into theta n minus 1 space. So they're like Seagull category objects in theta n minus 1 space. This should be complete Seagull objects. And then this should be equivalent to the theta n spaces. And so where this is at, so this is a theorem of myself with Charles Resk. And this is still a work in progress. This is on my to-do list to get done at the MSRI this semester. So I'll just finish. There are lots and lots of other approaches being done out there for infinity n categories and comparisons and all kinds of stuff. And I'd be happy to talk about them more, but I think so there's time for at least a couple questions. I'll stop here.